Geometry students, we're getting into Unit 4. Going to do our review, but looking at it, looking back at it, there is a ton of material in Unit 4. So we're going to break it down into most likely what's going to turn into 3 separate chunks and look at it a few pieces at a time. Okay, so we were getting into the very basics of polygons and their properties and things like that, and there's just a lot of stuff, as you'll see over the next few days. Anyway, we started off with types of triangles. And of course, we came across our very first definition for how polygons are constructed. And of course, polygons are constructed out of line segments, which we refer to as the sides of the polygon. And where those line segments join together, we get a point, which we call a vertex, or the plural of the word vertex is vertices. Okay, when you have 3 line segments joining together at their endpoints, we have the most basic form of polygon that is available in Euclid's geometry, and that is the triangle. Okay, now for the very first time we saw really the naming of polygons, and just like everything else that we'd seen to this point in the year, you identify what type of a structure you are dealing with, in this case triangles, and with polygons you list off the vertices that are needed in order to construct that particular polygon. So if you have a 3-sided polygon like a triangle, you are going to need all 3 vertices to name them off to identify the polygon. Now typically it is put in alphabetical order, so the triangle you're looking at there is triangle ABC, but it can be listed in any order and still be accurate. Okay. Basic categorization of the triangles. We have a bunch of different category names for the size of the angle measurements that are in the triangle. Now hopefully you remember that in any triangle it will always have 2 acute angles. That's a property of all triangles. You will have 2 acute angles. What the third angle is doing will dictate what type of a triangle it is according to categorizing it by its angle measurements. So if the third angle of the triangle is also acute, then that is what we're going to call an acute triangle. If the third angle of the triangle is 90 degrees, we'll call that a right triangle. If the third angle of the triangle is obtuse, then we'll call that an obtuse triangle. And if all of our angles happen to measure exactly 60 degrees, then we will call that equilateral. I'm sorry, equiangular. Okay. Now we have some other categories that go along with triangles, this time dealing with their side lengths. Okay. And the vocabulary term meaning everything is different or nothing is congruent, more specifically, is scalene. So a scalene triangle is a triangle that has none of its sides congruent. If you have 2 sides of your triangle congruent, that's what we call isosceles. But we've stressed this term throughout the course of the year. Isosceles is a little bit of a dangerous term because it means not necessarily 2 sides are the same. It means at least 2 sides are the same. Okay, so literally, we usually use isosceles to mean 2 sides are the same, but be aware that it could be more than 2 and still be called isosceles. When 3 sides are the same, we have a specific name for that, and that is equilateral. So we have those different names for those triangles. Okay, now expanding the vocabulary into polygons. Okay, what we already saw a particular type of polygon, the triangle. And just generally speaking, a polygon is an enclosed figure that is composed entirely out of line segments. So the 4 that you see at the top there are polygons. However, the ones at the bottom are not polygons because they are either open, meaning they have not actually enclosed themselves. There's some type of a route into the interior of what would have been the polygon had it been enclosed, or perhaps you have circular type sides on your shape, so we cannot call it a polygon. Okay. We also saw a couple of different broad categories of polygons. These are what we refer to as concave or convex. And there's a couple of different ways to remember concave and convex. One is just kind of the general obvious type definition here, where convex is where if you were thinking about like the the perimeter of the polygon as a road, and you are, traveling along that road. Each time you get to a vertex, which would be a corner if you were on the road, you would have to turn exactly the same direction each and every time in order to stay on the road. Whereas concave, if you're traveling along that road, you may turn the same direction nearly all the time, but at some point you're going to have to turn the opposite direction to stay on the road. So that's one way of distinguishing between concave and convex. Another kind of general way of thinking about it is the idea, a lot of people think of concave and they see that word, that part of the word cave, and say, okay, well, it looks like part of the polygon is caved in, and convex does not have any side that is apparently caved in. So that's one way of remembering it. The official mathematical way of remembering the difference between concave and convex deals with what we call the diagonals of the polygon. Now, diagonals are what you get when you draw in all of the connecting line segments that basically connect any vertex of the polygon to any other non-consecutive vertex of the polygon. Okay, so in other words, we're not traveling from one vertex to the very next vertex. That would be one of the sides of the polygon. However, if we skip one vertex and travel through the open space in or around the polygon to get to the next vertex, that would be a diagonal. Okay, so mathematically speaking, if all of your diagonals that are possible are contained within the figure itself, then that is what we're going to call a convex polygon. However, if you are able to get even one diagonal to travel outside of the polygon, then that is going to be concave. Okay, now our general categories, of course, we'd already seen the three-sided polygon, which is, of course, the triangle. Four-sided polygon, we spent a ton of time this year working on the four-sided polygons, but just generally speaking, we called them quadrilaterals. And, of course, if you have 5 sides on your polygon, that is a pentagon. If you have 6 sides on your polygon, that's what we refer to as a hexagon. 7 sides is a heptagon. You will actually see that one incorrectly named, even all over the internet, as a septagon, but it is heptagon with an H is the correct vocabulary there. 8-sided, most people know as an octagon. 9-sided is not a ninagon, it's a nonagon with an O. And 10-sided is a decagon. Now there are some other names for some of the shapes as you get to the larger numbers, but generally here we just kind of divert to a naming system. And that naming system basically encompasses, as you get the more and more numbers of sides, you simply identify however many numbers of sides and then put the root word gon behind it. So after you get past nonagon and decagon, you have an 11-gon and a 12-gon, 13-gon, 14-gon, and so on as high up as you need. Okay, now we'd already seen the idea of things being equilateral, meaning all of the sides are the same, and equiangular, meaning all of the angles are the same. However, if you are able to accomplish both of these at the same time in a single figure, then the term that we use for that is regular. You have a regular pentagon, or I'm sorry, regular polygon. Okay. Now properties. There's properties of triangles. There's a ton of things that are special about triangles, and we actually spent a good bit of time talking about the triangles and all the little things that they have to have happen with them. Okay, so let's take a look at some of this stuff. One of the first things that we looked at was the definitive connection between what is going on with the angle measurements of a triangle and what's going on with the side measurements of a triangle. And just in general, what we found right off the bat was that the largest side of the triangle and the largest angle of the triangle are always positioned predictably within the triangle, and they are always positioned opposite of each other within the triangle. The same thing is going to be true for the smallest angle in the triangle and the largest side in the triangle. They will always be across from each other. And that holds true also for if you get, if it's a tie, if you end up with two side lengths that are the same, that are congruent to each other, you're going to end up with two angle measurements that are congruent to each other, and they will be positioned across from them each other in the triangle. Okay, so that's a very simple property, and we've used it plenty of times this year. Okay, another one that we've used plenty of times is the interior angles of a triangle rule. And this one actually turned out to be a small part of a much larger rule that we got into here before too long. But the interior angles of a triangle always add up to be 180 degrees. So if you know what's going on with two angles of a triangle, you can very easily find out what's going on with the remaining angle. Okay, another one that we looked pretty deeply at was the triangle inequality theorem. Okay, this one's a really important one, and they do like to try to get you on this one from time to time. The triangle inequality theorem basically guarantees that for any two side lengths that you have in a triangle, okay, any two side lengths must always add together to be larger than the length of the third side of the triangle. And that has to apply for any combinations of two sides that you can add up to try to equal the third side. But most specifically, we are concerned with it with the two smallest side lengths trying to add up to be larger than the length of the largest side. If the triangle inequality theorem is going to fail anywhere, it's going to fail right there, trying to add the two little guys up to be larger than the big guy. Okay, so we looked at exactly what happens when the triangle inequality theorem fails. Okay, and we've worked several examples on that. Okay, now the way that the triangle inequality theorem is used more often than not is to try to determine what restrictions an unknown third side length must have on it. So if you know what's going on with two of the side lengths, but the third side is completely unknown, we can still place some boundaries on how big that side must be, in the sense that we can say how much, what is the smallest length that the side could be, and also what is the largest possible length that the side could be. And it's the triangle inequality theorem, basically in a nutshell, but only with an unknown value in this particular case. So like the example you're looking at the middle of the screen there, we have two side lengths that we do know, 5 and 7, and we have an unknown third side, x, that is unknown. So the three different ways those three guys can be added up is 5 plus 7, and 7 plus x, and x plus 5. And the triangle inequality theorem guarantees that when you add those two guys up, that must be greater than whatever the length of the third side is. Now, as you can see there on the left side and the right side, we end up with two good inequalities. 12 must be larger than the unknown side length, so 12 is as big as it could possibly get. It's got to be smaller than that. And then on the right side, we have x is greater than 2, which means that the side length has to be larger than the value of 2. Now you see we also get a negative value, and since there's no such thing as a negative side length in a polygon, we disregard that one. But anyway, that leaves you with two good inequalities, and that kind of targets the area that this unknown side length must be. It has to be larger than 2 units, but smaller than 12 units. Anything outside of those boundaries or on those boundaries, you're going to end up with 3 line segments that cannot connect to each other end to end, so you will not end up with a triangle. So you might want to look back at some of the examples, or maybe pull up that video if the triangle inequality theorem is still a mystery to you. And the last thing we're going to look at in this first little section of Unit 4, like I said, there's a lot of information in Unit 4, is just generally speaking polygon congruence. Now, you guys learned what congruent polygons were back in junior high. Y'all called them same size, same shape. And that's true. But in high school, we need to know what causes things to be the same size, what causes things to be the same shape. And that deals specifically with the corresponding angle measurements and the corresponding side lengths. Okay, so if you have corresponding angles, if all of your corresponding angles are congruent, then that is what's going to actually cause your figure to have the same shape. If you start getting angle measurements that are not matching up, that's going to open and close the figure up, and you will end up with differing shapes. Now, the corresponding side lengths all being the same, that's what's going to cause you to have the same sized figure. So that's what causes the same size. Okay, when you get all that happening all at the same time, you end up with congruent polygons. Now, the real key to all of this is not understanding the definition. The key to this one is being able to match up everything. Both those definitions, both those statements use the words corresponding. Okay, so we had to take great care to figure out what corresponded to what, and the thing that we kind of we really emphasized was that things do not correspond to each other based upon the way that they're sitting. Like these two triangles you're looking at now, obviously the 90-degree angle at the top does correspond to the 90-degree angle at the top from the red triangle to the blue triangle, but they do not correspond because they're both at the top. We could very easily take one of those triangles and rotate it or reflect it or do something. Okay, so it's important that when you're looking for things that correspond, you don't look necessarily geographically in the picture. You look for similar properties from one figure to the next. So the two triangles you're looking at now, the 90-degree angle still corresponds to the 90-degree angle because they have the same properties, not because they are sitting in the same locations. Okay, now when it comes time to name your congruent polygons, you've already identified that all your corresponding angles are congruent and all of your corresponding sides are congruent. It's time to make a statement saying that your figures are congruent. Okay, so just like always, you identify, hey, I've got triangle, and I listed at the bottom there BAC. Okay, how did I decide that it was going to be in that order? B, then A, then C? Well, it really doesn't matter. The important thing is once that order is established by the name of the first polygon, you absolutely have to follow that exact same order when you name the second polygon. So if we're going to list vertex B first on the left-hand triangle, then we got to figure out what corresponds to vertex B in the right-hand polygon. In this case, it was Z. So B is listed first, Z is listed first. That means B and Z are corresponding vertices. And then from B, we traveled along the side length to vertex A. So on the other triangle, we have to do the same thing. Figure out what corresponds to vertex A in the other triangle, and it happened to be vertex Y. So B then A corresponds to Z then Y, and then the same thing for C and X. Okay, so naming the polygons is kind of the tricky part, and you just got to pay attention. Make sure you get all your vertices lined up. And the important thing to be able to do on that is once you understand that that's the system, then when they gave you an example like this one that we went through, where they said, hey, pentagon ABCDE is congruent to pentagon FGHIJ, we automatically know by the way that the pentagons are labeled, the order that those vertices are written down, we know exactly what corresponds to what. We know exactly which angles are going to be congruent, which side lengths are going to be congruent. They have communicated a ton of information with us by simply us knowing the rule for how to read these vertices that are written down. Okay, so that's kind of the first third of the information. The remaining two portions that we're going to get into for Unit 4 will deal with the ideas of triangle congruency and triangle similarity. And as you may remember, there's a bunch of little shortcut rules and stuff like that that go along with it. Okay, so we're taking it in small chunks. There is a ton of information in Unit 4, but there is the first chunk.